Hi, everyone. Uh, Hopefully, the audio and video is clear to all of you. Can you please respond once in YouTube so that I can see your response and we can start the session immediately? Yes, I'm waiting for your response. Okay. So let me first make it very clear in what way this session, the sum of series, okay, and this session, what way this will add value to your GATE 22 preparation. Okay. See, what turns out is if you see the past year question papers, I can say out of 100 marks, around 60 marks of the questions are of kind of predicted model questions. Like in every subject, in every chapters, there are some model of questions from where very frequently questions are being targeted in the GATE exams. Okay, so based on the past year of question papers of GATE and my personal teaching experience of around 10 years, I have selected some questions which is definitely going to add value to your preparation, and it is kind of a revision for you people. Okay, so the first thing is in the digital circuit subjects, as you see, there are, if you see the screen, there are total 14 chapters, right? Ranging from number system, Boolean algebra, logic gates, K-map, combinatorial circuits, binary codes, latches, flip-flops, registers, counters, finite state machine, data converters, logic family, and semiconductor memories. Right? Sir, will this be only questions? Mostly, yes. 80% is like question solving and 20% some kind of, brush up of the theoretical concept. But of course, it is, I'm not going to explain everything in very detailed way. And I assume like the students who are listening to this session, you have some basics. The basics of the subject is known to you. You are kind of revising the things. Okay. That is what I'm assuming in this session. Well, so this book which you are seeing in your screen, this is our GATE Forum handbook. Okay. And this 14 chapters, the sequence in which you are able to see this, if you are if you are my students, you might have seen this is the same sequence I used to follow in my live classes. If you open your notes, in this sequence only, I have completed your course, isn't it? So, so what I have done is, I have two files. One file is for this, for this handbook, and the other one is basically the question selections which I have done. Okay. So starting with, so one by one we'll be doing. So in this one, the first topic is number system. Okay. So this number system, okay, this is what first we are going to see. Then Boolean algebra. Okay. So let us try to complete these two topics today. And if possible, we'll see the third one as well. Okay. The logic gates. Let's see. I will not make this session so lengthy, right? So it should be around 1 hour to 1 hour 15 minutes at max, but it should be intensive session. That's all. So the first thing is, in this number system, if you see this one, what you're observing in the screen, like in the number systems, we have basically 6 concepts from where questions are being asked very frequently. So the first one is based on conversion. Okay. And the second one is based on finding complement of a number. Third one is based on representation of negative numbers using sign number concepts. Fourth one is based on concept of plus 0 and minus 0. Fifth one is based on range of numbers using n bits. And the sixth one is based on overflow concepts. Okay. So if you go through all the 35 years of question papers of any competitive exams, particularly GATE, so 95% of the questions of number system chapters will fall in this category. As I said, I'm going to explain, or I'm going to take up those questions and concepts which are frequently asked. In every year GATE papers, there is a scope to ask some skill-based questions. For that, you need skill, or what we say in Hindi, dimag, right? Such kind of questions, nobody can predict, but what can be predicted, that's what we are going to see. Okay. So first, let me start with this conversion. Okay. So let us first start with this conversion. So basically, like this, any number system. Okay. So some concepts, let me give you. If a number system base is B or base is R, it means it is having R number of distinct symbols, right? So if you see any number system associates some radix and base, if a radix of a number is R, it means corresponding number comprises of R number of distinct symbols, that is the digit from 0 to R minus 1. Okay. And the property of this radix or base is it is always a positive integer. It's always a positive integers. But what happens is depending on situations. Okay. So we have these situations to convert to convert one model of numbers to other model of the numbers. In other words, one base numbers can be converted to other base numbers. From this category, questions are being asked. So we are going to see some questions based on this. So let us take the first questions, okay, which is this one. So actually there are three models you can say. The first model is some random base x should be converted to base 10. Second model is some base 10 number will be converted to some random base. And the third model is one number system base can be converted to other one. So let's start with the first one, okay? So I'm not saying that these questions are very challenging questions and very logical and tough question I have taken. That is what not the intention of this session. But such kind of questions has been asked, and there is a high chance in the upcoming GATE exam also you may get some questions like this. And intentionally I have taken these numbers where we have the integer part as well as the fractional part. So you people also please try to solve this and respond the answers. So what is the method to answer such kind of questions? If you have some base like base 16, you have to convert this into base 10, right? So how do you do? So you have this base 16. So here basically this x is equals to 16, right? So base x has to be converted to base 10. The logic is very simple. In such kind of cases, you just have to expand the polynomial. So you know very well, a stands for 10 into, so this is 16, okay, 16 power 0, 16 power 1, and this is 16 power 2. So a is 16, a is 10, 10 into 16 square, plus what is f? F is 15. So 15 into 16, plus what is 3? 3 into 16 power 0, plus 1 into 16 power minus 1, plus 5 into 16 power minus 2. Okay. If you sum this, okay, take a calci and you simplify this, the answer what you're going to get is 2860.08203.125. Okay. So this numbers, which is AF 3.15 base 16, is equivalent to this numbers at base 10. So this calculation will be quite boring if I'm again explaining the calculation, but this is what the methods. You have some random base. Okay, base is 16 in this case. This base can be 6, 7, 8, 9, whatever it might be. You have to convert it into base 10. Simply expand that polynomial with the corresponding base. So it is the base is 16. You simply expand this polynomial with 16 powers. So this is what is the answers. 2860.08 something. So that's the first questions. I'm not going to spend so much of time. And this one, the second question is, it is base 10 to base x. So in this case, the value of x is basically 8. So you have a number in base 10. Again, we have integer part and the fractional part. And I want to convert this into its equivalent base 8 forms. In the previous model, we have just expanded the polynomial. In this case, we have to do the continuous division. As you know, we have to deal the integer part separately, which is continuous division, and the fractional part separately, which is continuous multiplications. So let's see how do you do this. You will also please try to do. So first, I'm taking this 234, and then we'll take this fraction parts. We'll finding their equivalent base 8 forms separately, and together we'll write at the end. So 234, okay, I have to convert to base 8, right? So I'll be dividing with 8. So if you see, it is 8, 8, 16, and this is 9, right? So remainder is 2. then I have 8, then it is 3, 24, the remainder is 5. Then 8, it is 0, and this is 3. So that means, so how do you write this? So we write this in the bottom to top approach. So we'll see the end results at the end, okay? But this 234, you have to do like this. So no matter how big the number is or whatever the the number, if it is in base 10, if you want to convert this into some other base, like base 8, base 7, base 16, whatever it is, you divide that number repeatedly with the desired base. The desired base is x here, that is 8. So I'm dividing with 8. If this number would have been 7, I would have divided with 7. So this is how you deal with the integer part. So how do you deal with the fractional parts? So this fractional part, I'll be doing continuous multiplication. So 0.1285 into 8. So if you do it, so this is coming 1.0280, right? So what is the logic to simplify this? So this always what you do is if this integer part which is coming here, that is 1, in this case, you simply keep it out and then you always make it 0. So that means I have taken this 1 and then I'll be taking this 0. Then I'll be multiplying with 8. So if I multiply with 8, so how much I'll get? I'll get this is 0.2240. So this is 0. If this could have been, let's say, if this instead of 0, I'd have got 3, I'd have taken this 3 out and I'd have taken it is 0. But in this case, automatically it is coming 0, so no need. So again, I'm multiplying with 8. So from where this 8 is coming, this 8 is coming from here, okay? So this, if you multiply, so this is coming 1.7920. You can see here, again, this 1 is coming. So this one I'm taking out, I'll make it 0. Again, you multiply with 8. If you're multiplying with 8, so this number is coming 6.3360. So this 6, you again take it out and you make this is 0. So you have to always make it 0. Whichever number is coming, you simply take it out. So I'm multiplying with 8. So if I'm multiplying with 8, so this is coming 2.6880, right? So this 2 is coming out. So this is again 0. You again multiply with 8. So like this, you have to continue. Like in the previous case, we have done for the bottom to top approach. In this case, these numbers which I'm taking out, so that has to be taken as top to bottom approach. That means this 234.1285, one second. This 234.1285, okay, which is in base, how much? 10. So this is equivalent to this 234 corresponds to, you can see this 352, and this 1285. So this is this way. So 10162. What is the base? Base is 8. So this is how we deal with this. So 352.10162 ... So it is still continuing, right? We haven't got 0000. If we got 0000, that would have been the end. Otherwise, you have to continue this way. So this is what your question number 2. Okay. So the third model is base x to base y. So previous two cases, what we have seen is basically 2 cases: base x to base 10, base 10 to base x. That is what we have seen, right? So now here it is base x to base y. That means base 10 is nowhere, right? So although there are some other way, okay, one of the wise technique is, because we human beings are habituated to use the base 10 number system, you make use this base 10 number system as the intermediate numbers. So what I'll be doing is, so the first thing I'll be doing, I'll be converting this 18.6, which is in base 9. I'll be getting what is the base 10 equivalents. And then this base 10 equivalent, I'll be finding its base 11 equivalent, because ultimately I have to find the base 11 equivalents. So here, so the previous 2 models will definitely help us. So here I have to convert a base 9 into base 10, and again base 10 into base 11. So how do you convert this base 9 into base 10? Just polynomial expansion. And when you are converting this base 10 to base 11, you have to go by again that continuous division and multiplication methods. So this model is basically combination of the previous 2 model of the questions. So Ajay said, so This 18.6 base 9, what is it in base 10? 1 into 9 power. Okay, so minus 1, sorry, plus 1, right? Plus 8 into 9 power 0 plus 6 into 9 power minus 1, right? So this is 9 power 0, 9 power 1, 9 power minus 1. So if you find it out, so this number is coming 17.666. So this is coming 17.666. Okay, so this you got. Then because you need its base 11 equivalents, so this, the integer part 17 has to be divided repeatedly by 11. And this 6 is the fractional part, you have to multiply with 11 continuously. So then if I do that one, so 17 if I do by 11, so this is coming 1, the remainder is 6. Again, if you do 11, so this is 0, and this is basically 1. So this is what the integer part, and the fractional part, 0.666. You have to multiply by 11. If you multiply by 11, so this is coming 7.326. As I said, you have to always make 0. So this 7, I'm taking it out, so I'm making it 0. So again, I'll multiply with 11 because my required base is 11 in this case. If I multiply with 11, so this is coming 3.586. Hopefully all of you are getting same, 3.586. So this 3, you have to again take it. I'm making this is 0. So again, you have to multiply with 11. So if you multiply with 11, you're getting it is 6.446. So this 6, you have to take it out. Again, you make it 0, and so on and so forth. So how do you take the answer finally? So in the integer part, bottom to top, and in the fractional part, this is top to bottom. That means what I can say is 18.6 base 9 is equivalent to 17.66 base 10. And this is equivalent to 16, right? This is 016, which is 16 points. This way, if I see, first I'm getting 7, then I'm getting 3, then I'm getting 6, and so on and so forth. 736 ... This is base 11 equivalent. Okay. So this is what is the questions which are based on the number system conversion. Such kind of questions in GATE exam, it has been asked and it will be asked. This is also one of the frequent model asked questions, and this question is asked in the Civil Service Examination 2006. Now, what is this question is? So the question is, you have this square root of 224, and this is equivalent to 13 in some base r. So the question is, what is this base r? So how do you find it? Any idea how to find this? Yes, all of you please respond. Square root of 224 is equals to 13 some base r. What is the value of r? So what we'll be doing is, again, we don't know what is this base r, right? And because the people are comfortable to deal the algebra in base 10, so again, this base r I'll be converting into base 10. So Mayank is saying squaring both sides. You cannot square it because you don't know whether it is in base 10 or what. So the first task is, I'll be finding what is the base 10 equivalent of this 224r. So this is r. So what is it in base 10 forms? So r can be 4, 5, 6, whatever it is. How do I get the base 10 equivalent? This is 2r square. That is the same polynomial expansion. This is 2r plus 4. So this is equivalent to base 10. Similarly, 13r, okay, if I write in the base 10 formats, it is 1 into r, that is r, plus 3 into r power 0 is 3. So what I can say is, so this 224r and this 13, so this I am writing in the base 10 equivalents. Okay, so I can say here square root of 2r square plus 2r plus 4 is equals to r plus 3. So this equation is in base 10 now because we have converted the number into base 10. This equation, which is given originally, it may not be in base 10. So now we can do the square, but I cannot apply the square directly here because I don't know whether it is base 10 or not. So if I square both sides now, so the equation is 2r square plus 2r plus 4 is equals to r plus 3 whole square, which is r square plus 6r plus 9. So if you simplify this, the equation is r square minus 4r minus 5 equals to 0. And if you factorize this, r minus 5 into r plus 1 equals to 0. So r having two value, r value is 5, r value is minus 1. But as I said, the base or radix is always a positive integer. So answer has to be 5. Minus 1, although we are getting some value, but minus 1 can't be answered because base is always a real and positive numbers. Base cannot be complex, base cannot be negative, base cannot be fractional. Okay. So if you see my list, so the first model of question which I've given is based on conversion. And based on conversions, I think around 4 or 5 questions we have seen. Couple of more questions that will take up. So here I'm putting a tick marks. So questions based on this number system conversion we have seen. Now the next question which I'm going to show is based on finding complement of a numbers. So here, first thing I would like you to brush up some concepts. How do you find the complement of numbers? Okay. So I think hopefully students, all of you who have our Gate Forum annual students, you have this handbook soft copy. Okay. So this is personally written by me and all the details. Okay. All minute formula. So this is, very ideal for your revision purpose. That way I have designed it. So let's first brush up this complement number systems in a very brief manner, and then I'll be taking the questions based on this. Okay, so why this complement is necessary? Because complement is necessary to express the negative numbers. In computers, we don't have options to put a negative sign. In pen and paper, we're putting a negative sign, but computers has to understand a number is positive or negative by using these complement numbers. Okay. So in simple language, if somebody asks you what is the purpose of complement number system, so you can say complement is used to obtain the negative equivalent of a number. So here the main thing is if you have base r, so this base r can have two possible complements. So here you can see one is the rs complements and one is r minus 1s complements. Okay. So let's say you have a number in base 6. Okay. So this number n can have two possible way to represent minus n. Why minus n? As I said, complement number system is used to represent the negative numbers. Okay. So this minus n can be represented using two way. One is this called this r minus 1s complement. One is called r's complements. So how do you get this r's complements? R's complement is obtained using this formula, r to the power n base 10 minus n base r. Okay. And how do you get r minus 1s complements? R minus 1s complement is same, r power n base 10 minus n base r minus r to the power minus n. If you make the comparison here, so the only thing which is extra in this case is the third term. Okay. So what I can say is in the last expression, that is in these expressions, if I add r power minus m, I'll be getting rs complement. That means in r power 1's complements, if I add these factors, I'll be getting the rs complement. But this is what the formula. But you should know what is this symbolic notation? What is the meaning of r, capital N, and small m? So here I have given here, r is the radix of the numbers, n is number of digits on integer part of n. Okay. Small n is number of digits in the integer part of n, and small m is number of digits on the fractional part of n, and n is number itself. Okay, so this is what is the meaning of the notations. So you have to memorize this formula, and let us take some questions where we'll be learning how do you make use of this formula. So to explain this, I have taken this particular questions, which is 124.36 base 8. So obtain its possible complements. So because the base is 8, so we have two possible complements. One is called the 8s complements. Okay. And one is the 7s complements. Rs complements and r minus 1s complements. So how do you get these 8s complements? So the formula says 8s complement means it is r's complements. So the formula says it is r power n base 10 minus n in base r, right? So here r is how much? R is nothing but 8. R is 8. R is what? R is nothing but this radix. Okay, this is 8. So this is your small r. And what is this small n? Small n is the number of digits in the integer part. So n is 3 here. And what is this m? Small m. Small m is the number of digits in the fractional part. So this is your fractional part. M is equals to 2 in this case. And what is n? N is nothing but the entire number. Entire number is n. So by formula, so this is r power n. So r is 8. 8 power n. N is 3. So 8 power 3. This is in base 10. Minus the numbers. Number 124.36. This is in base 8. Because the formula says this is in base r. So how much is it? So if you find it out, so 8 power 3, this is in base 10, this is 512 in base 10. And this, I'm leaving it a task to you. You please convert this into base 10. Otherwise, how do you do the subtraction? Both of the base should be same because we are comfortable to subtract in base 10 compared to 8. So I will definitely advise you to convert this base 8 into base 10. So if you do it, you'll be getting this is 84.46875. We have done the task. How to convert base 8 into base 10, we have seen. If you do the same process, this is what you're going to get. And if you simplify this, this answer is 653.42. 653.42. So this is, of course, in base 8 because we are dealing with base 8. So all the answer, what I'm going to get is base 8 formats. So I said possible complements. So possible complements are 8s complements, which is RS complements we have seen. And the second possibility is 7s complement, or which is R minus 1's complements. And coming to this R minus 1's complement, or which is 7s complements. So that is given by the formula what? R power n in base 10 minus n in base R minus R to the power minus m in base 10. That is what the formula. So in this case, if you see, so it is 8 power 3 base 10 minus 124.36 base 8 minus 8 to the power minus 2 in base 10 because m value is 2 in this case. If you do this, so this is again your 512 in base 10 and again the same, if you convert into base 10, it is 84.46875 base 10 and this if you convert it is 1 by 64. And if you simplify this, the overall answer is 653.41 and this is in base 8 again. This is in base 8. Okay, so this is what the answer is. So it is important to memorize this expression. This expression and this expression. So what is R's complements and what is R minus 1's complements? You should definitely memorize this. Hopefully, this is clear. Okay, fine. Having said that, okay. So if you see this, so this question which you have solved, this is based on finding complement of the numbers. So this model we have completed now, based on finding complement of numbers. So out of 6 models, the first 2 model is done. So now let us go into the third model. And the third model is based on representation of negative numbers using sign number concepts. Okay. So for that, again, I would like you to give some concepts and then I'll be taking questions. And this segment is the most important segment. So I'll be giving here 3 star, okay? Because questions are quite repeated in this model compared to the previous one. Are you facing any difficulty? Are you following or not? Okay. So we'll continue this within 2 minutes, okay? There is some technical issues. Let me simplify this. After 2 minutes, we'll again continue. Okay. So let's start it again. Audio, everything's fine? Yes. Can you respond? So, yeah. So the first two concepts are done. And the third concept is based on representation of this negative numbers using sign number concepts. Actually, we have this both negative as well as positive numbers in sign number concepts. But as again, so if you see the frequent model questions, yeah, we have again this negative number is much targeted compared to positive numbers. So we'll focus mostly on the negative numbers. So let me give you some concept first, and then we'll see. Okay. Well, so this table will give you enough information. So here, if you see, the first point is in unsigned numbers, signed numbers. So in unsigned numbers, only positive numbers can be represented. In unsigned numbers, only positive number can be represented. In signed number, both positive as well as negative number can be represented. In unsigned number, there is no sign bit concepts. We don't have any sign bit concepts. But in signed number, we have this sign bit concept. It is used to distinguish the positive and negative numbers. So there is no further classification on this category. Okay. But here we have classification. There are three classifications in sign number category. So this is sign magnitude representation. One is complements and two is complements. In all of these three possibilities, positive representation is same, but negative representation is different. Okay, so this table is giving you the summary, right? So unsigned number is only meant for positive numbers. Signed number is meant for positive and negative numbers. No sign bit concepts. Here we have sign bit concepts. No further classifications. We have three classifications. In all the three classifications, positive number representation is same, but negative number representation is different. So you have to read the question very carefully, what they're asking. Okay, for example, so this is what you see here. So I have taken here represent plus 12 and minus 12 using unsigned number representation. Okay, so if I explain you what is plus 12, so 12 in binary form is 1100. So simply I have written here 1100. And if I say what is minus 12 in unsigned number, it cannot be represented using unsigned number representation because we said here it is not valid for negative numbers. It is meant for only positive numbers. So negative number cannot be represented. But this is what the next question is very important here, right? So here I'll basically highlight all these three categories. So here the question is represent plus 12 and minus 12 using sign number representation. So as I said, plus 12 in all these three categories same, minus 12 in all these three categories are different. So how do you represent plus 12 in all these three categories? So the logic is very simple. 12, you'll be writing 1100 in binary form. So for plus, you have to put a 0. That's all. So this is what the same for all the three categories. So if you see, this plus 12 is 0, 1100, right? So this is same for all three categories. So plus 12 representation, all three possible forms are same. Here MSB 0. This is the sign bit. MSB is 0 for positive sign. The rest 4 bits are normal binary representation of 12. Very simple, right? But this is what is the important segment, minus 12. So how do you represent this minus 12 in all the possible formats? What are the formats? One is the sign magnitude forms. One is the ones complement form. One is the twos complement form. So first thing is coming to the sign magnitude. Sign magnitude, what we'll be doing is, so for 12, we'll be writing 1100. And if I put a minus sign here, I'll be putting a 1 here. That's all. So that's why you are getting here. It is 1100. So out of this 1100, 1100 is for 12 and the MSB 1 is for minus. Okay. That's what the point is. But in ones complement, what we'll be doing is, in ones complements, we'll be taking the 1's complement of plus 12. So plus 12, we have said it is 0, 1, 1, 0, 0. So you have to take 1's complement of this 0, 1, 1, 0, 0, 0, 1, 1, 0, 0. So you see here, 1's complement of plus 12, which is 1's complement of 0, 1, 1, 0, 0, which is coming 1, 0, 0, 1, 1. So that's why he said here. So 1's complement representation of plus 12 is 1, 0, 0, 1, 1. Similarly, if I ask you what is for 2's complement representation of this minus 12. So you have to take 2's complement of plus 12. So 2's complement of plus 12 is again these numbers. If you find 2's complement of this, you are getting this. Okay. So here you see here, in all these three formats, if I see the sign bit is 1 here, the sign bit is 1 here, the sign bit is 1 here. In all the three cases, the sign bit is 1. So negative numbers, one of the common point is the sign bit are same 1, 1, and 1 in all three cases. So in representation of minus 12, sign bit at the MSB 1 in all three forms and representation are different. So if I say minus 12 can have three representation. One is this in sign magnitude, this in 1s, and this in 2s. So you have to read the question very carefully. What is the representation of minus 12? In sign form means there are three answers. Answer can be this, this, and this. What is the representation of minus 12 in 2's complement? This is the answer. What is the representation of minus 12 using 1s complement? This is the answer. What is the representation of minus 12 using sign magnitude? This is the answer. This way you have to deal with it. Okay, fine. So in GATE exam, okay, what kind of questions are being targeted? Let's see. So for that, I have selected some questions, these questions. Such kind of questions are coming repeatedly in the GATE exams. So here the question is in the reverse way. So the question is, obtain the decimal equivalent of following. So three cases I have taken. One is in the sign magnitude form, one is in the 1s complement form, one is in 2's complement form. So this is very important. You have to read the question carefully. In which particular format they have given the corresponding questions, right? If you see carefully in these cases, in all the three cases, the number is same. I mean, this number, and this number, these numbers are same. So the same number, I'm asking you in different forms. So if this is the numbers in sign magnitude, what is the answer? If this is the numbers in 1's complement, what is the answer? This is the numbers in 2's complement, what is the answer? That way, I'm asking you. Okay. So in sign magnitude form, it is very straightforward. So what I'll be doing is, because the MSB is 1, so for this, I'm putting a minus sign here. So in sign magnitude form, this is the method I'm saying. If you see it is sign magnitudes, so for this MSB, it is 1, so I'm putting in negative numbers. And then you simply find what is the decimal equivalent of the rest of the numbers. So if you find the decimal equivalent of the rest of the numbers, that is basically 26. So overall, this is basically minus of 26. Again, I'm repeating, for this MSB, I'm putting a negative sign. Except this MSB, what is the decimal equivalent of this binary numbers? You find it. So the decimal equivalent of this binary numbers, except the MSB 26. So overall answer is minus of 26. Okay. Now coming to the second questions, if the same number, if it is in 1's complement form, then what are the answers? Again, the same story. Okay. So for this is MSB. MSB is 1. So I'm putting a negative sign. Okay. I'm putting a negative sign. Then the method to find it is decimal equivalent of 1's complement of this numbers. Decimal equivalent of 1's complement, this overall number, which is 1, 0, 1, 1, 0, 1, 0. Decimal equivalent of 1's complement of this entire number. So this minus I'm bringing from this one, and then decimal equivalent 1's complement of this. So this is equivalent to minus of. So decimal equivalent of, what is the 1's complement of these numbers? 0, 1, 0, 0, 1, 0, 1. So just you have to flip the 1 to 0 and 0 to 1. So if it is 1, 0, 1, 1, 0, 1, 0. So if you find its 1's complement, this is 0, 1, 0, 0, 1, 0, 1. Right? And if you find what is the decimal equivalent of this binary number, this is coming 37. So overall answer is minus of 37. So this is what is the minus. And if you find what is the decimal equivalent of this binary numbers, this is 37. So the answer is minus 37. And this way, again, the method is similar. Again, this is 1. So I'm putting a negative sign. Then the method is decimal equivalent of 2's complement of this overall number, which is 1, 0, 1, 1, 0, 1, 0. So which is equivalent to minus of, this is decimal equivalent of. So what is the 2's complement of this? You find the 2's complement, this is 0, this is 1, this is 1, 0, 0, 1, and 0. You find the decimal equivalent of these numbers. So this is minus of, you find it out. So this is coming 38. So the answer is minus of 38. Okay. I'll suggest you go through the previous year GATE question papers of last 3-4 years, particularly in electronics branch. You see there are 2-3 questions. Okay. from this model questions. Anirudh is asking why we are not omitting the MSB in one's complement. Why we are not omitting MSB in one's complement? Why we should omit? I mean, where is the question? I'm not getting a question, Anirudh, actually. Anyway, this is the methods, okay? So the answer, so what I can say is the number I have given is 1011010. This is what the number I have given, right? So this number, if I say it is sign magnitude, answer is minus 26. This number, if I say it is in 1s, the answer is minus of 37. The same number, if I say it is in 2s, the answer is minus of 38. So you have to see the question carefully. The given number is in which forms, whether it is in sign magnitude form, 1s forms, or 2s form. So answer will vary. So this year, I think one question they have given in terms of PQR and some twist they have played, but ultimately this is what the technique is. Hopefully this is clear. Well, so next is, this is what is one important concept, the concept of plus 0 and minus 0. So with this, I have completed this, this one I have completed, right? The third concept. And fourth concept is based on concept of plus 0, minus 0. So what is the concept of plus 0 and minus 0? See, in real life, in mathematics, we don't know what is plus 0, minus 0. It is simply 0 for us. But in this category, in this sign number representations, the three categories which we said, sign magnitude 1s and 2s, all these forms, we have to see carefully what is plus 0 and minus 0 concepts. So remember, so here the concept is something like this. So the concept is this one. Yeah. See, so the conclusion I'm just reading. 0 have unique representation in 2's complement format only, but 0 have different representation in 1s sign magnitude form and 1s and sign magnitude form. Okay. So the concept is in 2's complement forms, plus 0 and minus 0, they are same. In 2's complement form, plus 0 and minus 0, they are same. But in 1s complement and in sign magnitude form, okay, plus 0 and minus 0 are different. Okay, na? So in sign magnitude form, plus 0 is all zeros. So I have just, so with respect to 4 bits, you can take any bits. So in 4 bits, so sign bit is MSB. So 1 bit is gone. So rest 3 bits are used. So 0, 0, 0. So how do you represent, let's say if I say to represent 2, I mean plus 2 in sign magnitude form, what do you do? So 1, 0 is for 2, for this plus we'll be putting a 0. And if I say represent minus 2, again for this 2, I'll be using 1, 0, that is for 2. And for this minus, I'll be putting a 1 here. This is what we do, right? So same story. So here if I say you use for this plus 0, so what you do is for this plus I'm putting 0. And the binary equivalent of this 0 is 0, 0, 0. All right. And if I say what is minus 0, so again for this minus sign, we'll be putting 1, and this is 0, 0, and 0. So in sign magnitude form, if I use 4 bits, 1 bit is gone for sign bit and remaining 3 bits. This is what is the representation of plus 0, and this is what for minus 0. So what is the conclusions? So the conclusion is in sign magnitude form, we have 2 representation for 0. One is plus 0, one is minus 0. Same is the story in case of the 1s complement as well. So in 1's complement methods, what is the logic we said? I was explaining that plus 12 and minus 12 concept, right? So what is the story there I said? So the story is, how do you represent? So plus 0 means, plus means 0 and 0 means again, this is the same story. And if I say minus 0, you have to take 1's complement of this. If you take 1's complement of this, you get 1, 1, 1, 1. So plus 0 is all zeros, minus 0 is all ones. This is how plus 0 and minus 0 in 1's complement forms. In 2's complement form, how do you do? So plus 0 is anyway again same, okay? Minus 0 means you have to take 2's complement of these numbers. If you take 2's complement of all 0, again all zeros only, right? So what is the conclusion then? So in 2's complement form, plus 0 and minus 0 answer is same, right? And in 1's complement and in sign magnitude form, it is different. So you see here, this number and this number, this number and this number are not same. This number and this number are not same, but these two numbers are same. This is what just a concept, okay? So here I have just given that one, okay? So no questions, just I want to highlight the concepts. So I have just given this one. Okay, hopefully this is fine. So next one is range of numbers using n bits. Okay, and you see the previous question papers. So this question is also very important. I mean, frequently it is asked. So this is just a formula based questions. In the theory, I have given the logic how this formula are coming. Okay, but this formula you have to remember from exam point of view. So they will be asking you, if we give you 4 bits, let's say for example 4 bits. So what is the maximum positive numbers? What is the maximum negative numbers in sign magnitude form, in ones form, in twos forms? So in sign magnitude form, okay, if I use 4 bits, so here the n notation is meant for number of bits. N is meant for number of bits. So if you take n is equals to 4, okay, if you take n is equals to 4 here, so this is 16 minus 1. So sorry, here there is a correction. Please make a correction. So this is actually 2 to the power n minus 1. Sorry. Okay, so if I take n is equals to 4 in this case, so in this one it is 2 raised to power 4 minus 1, 2 raised to power 3 is 8, 8 minus 1 is 7. So this is minus 7 to plus 7. So same is the story for this. You can see here this formula, I mean this, sorry, this and this formula are same. So in this case also minus 7 to plus 7. But in the next case, in 2's complement, so we don't have this minus 1 here, right? So if you simply substitute here, n equals to 4, it is minus 2 raised to power 3, which is minus 8. So this is minus 8 to plus 7. So from this 3 formula also, in GATE exam, we have good number of questions. You can go through it. Okay. So this is what also I wanted to discuss. So if you see this least concept of plus 0, minus 0, we have seen, and based off range of numbers using n bits, we have seen. And the last category of questions, what you're getting from this segment is the question which is based on the overflow. So let me summarize this. What is this concept of overflow? If you know how to do the arithmetic using sign concepts, sign bit concepts, you must have learned this. In my classes, I have taught it. So in case you have forgotten it, so please listen this, you will brush up things. Otherwise, if you have a little bit basic still, you listen this, you will understand. So when we do addition, subtractions of decimal numbers using 1s or 2's complement methods, we may come across overflow conditions. Okay, so these 2 points are important. Overflow never happens if we add 2 opposite sign numbers. It may happen if we add 2 same sign numbers. That means if I have a numbers 2 and if I'm adding with minus 7. So if you're adding 2 opposite sign number, one is positive number, one is negative numbers. Okay, the overflow will never happen. Okay, so overflow may come into pictures if we add 2 same sign numbers. It may happen if we add 2 same sign numbers. That is, you are adding 2 positive numbers or 2 negative. If you are doing, let's say, plus 7 and plus 8, or if you are doing minus 6, minus 6. If you are adding 2 same sign numbers, both are positive or both are negative, in that case, overflow may happen. But it will never happen if you are adding 2 opposite sign numbers. See, this is the second point. If we add 2 same sign numbers, but the result is of opposite sign, then we say overflow has occurred. So the situation is something like this. Let's say we are adding 2 positive numbers. We expect the answer is positive. If we are adding 2 negative numbers, answer will be negative. So let's say if we are adding 6 with 7, so answer is plus 13. If we are adding minus 7 with minus 9, answer is minus 16. So no matter how big or how small the number is, if you know both of the sign are same, that is both are positive or both are negative, it means the corresponding answer should also be positive or negative. It should never happen if we are adding 2 same sign numbers and the bit is also same, then overflow will not happen. But if you are adding 2 positive number, the answer is negative, or if you are adding 2 negative number, answer is positive, that means overflow is happening. What is this overflow actually? Overflow means, so for the addition purpose, whatever the number of bit you have used, that is not sufficient. For example, so let's say I have a number x. So for x, I have used 3 bits. And let's say I have a number y. For y also, I have used 3 bits. Now I'm saying that both this x and y, they are positive numbers. And if you're adding, I'm getting the number plus z. So let's say the minimum requirement of this Z is, let's say, 4 bits. That means to represent the number, we need basically 4 bits. So my requirement is 4 bit to represent Z, but already I'm using 3 bits. That means your requirement is 4, but you are using 3 bits. So of course, then if the requirement is for using 3 bits, 3 bits will not be enough to represent this 4-bit number. So in that case, we say the overflow is happening. Okay. So here, this is what I have illustrated, and based on these questions are being framed. I mean, the same thing what I said. So here I'm just giving in the form of some kind of equation, you can say. So this is something like this. Let's say n1 plus n2 equals to n3. X is sine bit of n1, y is sine bit of n2, z is sine bit of n3. Okay, then specify the condition overflow. Okay, so the situation is something like this. I have n1, I have n2, and if I add it, I'm getting n3. So n1 having sine bit x, and then we have the numbers. N2 having sine bit y, then we have the numbers. If I add it, the sine bit is z, and then we have the numbers. Okay, so here I'm saying if x is not equals to y, okay, then no chance of overflow. So x and y are not equal means they are two opposite sign numbers. So in that case, overflow will not happen. But if x equals to y, if both of these are same, that means both are positive or both are negative, overflow may or may not be. I mean, it is not like every case you will get overflow. It may happen, it may not happen. Okay. If x equals to y equal to z, if x, y, and z are same, that means if you're adding two positive number, answer is positive. Or if you're adding two negative numbers, answer is negative. Then there is no overflow. But if the reverse thing happens, that is x and y are same, but z is opposite. So x is positive, y is positive, z is negative. Or x is negative, y is negative, z is positive. In this kind of cases, overflow exists. Okay, so this is what is the concept of this overflow. So here, one question I would like to solve. Yeah, this questions. This question has been asked in IES 2008. Okay, see the question. Two 2's complement numbers having sign bit x and y are added, and the sign bit of the result is z. Okay, which Boolean function indicates the occurrence of the overflow? Okay, so you need some little bit of Boolean algebra concepts. So what I'm doing is, so I'm writing the combination of x, y, and z, right? So the story is again kind of same. So you have a number n1 whose sign bit is x. You have a number n2 whose sign bit is y, and you are adding it. You are getting the number n3. Its sign bit is z. So in terms of x, y, z, they're asking what is the expression of the overflow. So how do you get it? If you understood the logic, you can easily answer. Otherwise, what you do is you make a table. You make a table x, y, and z. And here I'm making a column for O. So I'm writing all the 8 possible combinations. So you see here, in the first two cases, okay, x, y, and z are same. Okay, x, y, and z are same. Sorry. So overflow will not happen. I'm putting 0. When overflow will happen, I'll put it 1. In the second case, x and y are 0, 0. That means x and y are 0, 0, but z is 1. So you see here, there is a change, right? We expect x, y, and z. So what are the conditions? If x equals to y equals to z, then O equals to 0. If x equals to y, and if this is not equals to z, then overflow O is equals to 1. That's what I'm doing. So here, 0, 0, x, y, and z are same, it is 0, right? So here, x and y are same, it is not equals to z, it is 1. So in this case, x is not equals to y. X is not equal to y means what? These are two opposite sign numbers. So here I'm putting it 1, okay? And in this case, x is not equals to y. There is no chance of overflow, 0, 0. And same is the story for this as well. So you can see here, x and y are not same. In the below two cases, x, y are 1, 1, z is 0. So here, you are adding two negative numbers. 1, 1 means, sign bit is 1 means negative numbers. And the answer is positive now. So here are the overflow conditions. Here again, there is no overflow conditions because you're adding two negative numbers and z is sign bit is 1. That is again negative numbers. So only 2 cases out of 8 combinations, we are getting the answer 1. So if I ask you to write the expression of O, so the answer is, if you write in the mean term way, it is x bar y bar z, right? 0, 0, 1, x bar y bar z, plus it is x, y, and z bar. So if you see this, so the answer is option C. So C is the right answer for this question. Okay. So like this, you can expect questions. Some more questions I have taken. So let us try to solve these one by one. So this question is asked in, again, Civil Service Examination 2007. So some of you might be surprised. So how do you get civil service in exam in this kind of digital questions? So actually, electrical branch is there in the civil service, that in those days prior to 2010 and all. So they used to conduct examinations stream-wise, and stream-wise there are so many subjects like history, geography, anthropology, English, Hindi, like that. Electrical engineering is there and mechanical engineering is there in civil service, right? Those days the exam used to be conducted, and in their syllabus digital used to be there. Even today also, like once you pass the prelims, when you go to write mains, you have option to select this electrical engineering. But objective exam point of view, so those questions are not, we are not getting these, the exam pattern has been basically changed. If you see the history in the present day prelims exams, we don't get this technical segment. It is common for all of them. But if you're going for mains, you have option for 2 papers you can select from electrical engineering, where entire syllabus will be asked. Anyway, it's a different story. Let's see this one. All of you try to answer this. So the question is displayed on the screen. All of you try to answer. Let A is a numbers and B is a numbers, be 2, 8 be 2's complement numbers. What is their product in 2's complement form? Okay. So A is a numbers and B is a numbers. Okay. They are in 2's complement form. What is their product in 2's complements? How do you answer it? One thing is very clear. A sin bit is 1. It means A is a negative number. B sin bit is 0. That means a positive numbers. And we are multiplying a positive numbers with negative numbers. So the answer is negative numbers. And if it's negative number, the sin bit is 1. But anyway, in all the 4 options, all sin bits are 1. So we cannot eliminate any of this. We have to actually solve it. So the approach to solve this problem is, we'll be finding what is the decimal equivalent of this numbers. What is the decimal equivalent of this number? We'll be multiplying them. And whatever the answer I'll get in decimal forms, again, I'll be representing in 2's complement form. That's what I'll be doing. So if I have this 1, 1, 4, 1, and 1, 0, 1, 0, if this in 2's complement form, so for this one, I'll be getting a negative sign. Then decimal equivalent of 2's complement of the same methods. 1, 1, 1, 1, 1, 0, 1, 0, which is minus decimal equivalent of, what is the 2's complement of this? 0, 1. Then I'll flip all the bits. 1, 0, 0, 0, 0, 0, which is coming how much? Minus of 6. So this is 6 and we have negative sign. So A is equals to minus of 6. Similarly, what is this B? So B is any positive numbers. So this is, for this 0, I have plus, and then you have to find the decimal equivalent of the rest of the numbers. So this is 10. So B is your plus 10. So A is minus 6 and B is your plus 10. So what is their product? So A into B is minus 6 multiplied by plus 10. So we know the answer is minus 60. So what is minus 60 in 2's complement form? So how do you get it? So 60, if you find, what is the binary equivalent of 60 is 1, 1, 1, 1, 0, 0. Right? This is 60 in binary form. 8, 4, 2, 1. Then it is 16, 32. Yeah, 32, 16, 48, 48 and 12, 60. So this is 60. And what is plus 60? If I say plus 60, this is 0. And if I say what is minus 60, you have to take 2's complement of these numbers. If you take 2's complement of these numbers, so the answer is 0, 0, 0, 0, then 1, then 0, 0, 0, 1. So 1,000,000, 1,000. This is the answer. 1,000,000, 1,000. This is the answers. 1,000,000, 1,000. 1,000,000, 1,000 answers. Some of you have doubts, sir. So it seems option A is correct. If I see, yes, option A is correct. But the doubt is regarding this one. Sir, what about this one? This one you are not getting. I hope you know the sign bit extension concepts. What is the sign bit extension concepts? In 2's complement and 1's complement form, if I extend the sign bit any number of times towards left, it will not change the value of the original numbers. That means here the sign bit is 1. So this one, even if I copy here 10 times, 20 times, 100 times, so again it will represent the same minus 61. Okay, so the answer is option A in this case. Okay, so this was the questions. Let's see how many of you answer in this question. This is asked in Engineering Services 2011. Okay, so the question is, if 73 base x is equals to 54 base y, then what is the possible value of x and y? Okay, so this is the equation given. We have to get what is the possible value of x and y. So again, because I don't know what is x and y, so I'll be converting this into base 10. So if I convert base 10, it is 7x plus 3 is equals to, this is 5y plus 4. So the equation is 7x minus 5y. 7x minus 5y is equals to 1, isn't it? 7x minus 5y is equals to 1. We have only one equation. Then how do you get it? Then the only possibility is you go to the options. You see which option is satisfying this. Which option is satisfying this? Some of you are saying D. Is it D satisfying? Let's see. 7 into 8, 56, minus 5 into 11, 55 is 1. Yes, D is satisfying. This equation is satisfied by only option D. But tell me, what is the exact value of x and y for this? We can't have a unique answers because we have only one equation and two unknowns. Okay. So this is what the questions of the number systems. So today is the first session. Okay. So I'm not going to drag this session, for a longer period of time. And in the tomorrow sessions, we'll have Boolean algebra. And this is what is the content of Boolean algebra. Okay, we are going to see. Okay, so this content and all we'll see in the next class. So now let me take some questions. Okay, so like this is what is the model I'm going to follow in my entire this sum up series of digital in Gate Forum YouTube channels. Okay, so my approach will be, I'll be giving you a list like this, and in this list I'll be giving you the concepts. These are the concepts from where questions are being asked. I'll give you the corresponding theory background from our handbook, which is in a brief way I have presented, and I'll be giving the conclusive point there, and using that conclusions, some questions, which some of them I have my own creation, some of are from previous year question papers, some of them from few textbooks. So this kind of approach we are going to see. Hopefully, this session is helpful for you, and you are feeling it is definitely going to add value to your preparation. If you have any questions, please let me know. We'll chit chat for 5-10 minutes, and then I'll close this session for today. Yes, please. Anything you want to ask? Any suggestion you want to give? Any expectations do you have? Let me know. See, as I said, like nobody can explain you or help you out in the questions which are the skilled based questions. Okay, so skilled based questions you have to think yourself. But frequent model question you can ask. Moink is asking, sir, number system is important for Gate 22. See, I mean, there are total 14 topics. We can say, if you ask me in an overall sense, sir, whether number system is important, then I can say relatively from sequencer circuit, combination circuits, its chances are less. But nobody can deny, right? That's the point. Yes, one thing is true, for electrical stream, number system is not important. But for computer science and electronics and instrumentations, number system is important. Because if you see the previous year question papers of number systems, there are a good number of questions. Okay, so like this, I have planned the sessions for the entire syllabus. Okay, I mean, in the first phase, we have seen there are 14 chapters, right? These 14 chapters. So out of 14, one is done. It's not like every day I'll be taking one sessions and I'll be taking 14 sessions. They're not that way. Okay, we'll see. But my approach is to cover up all the topics. Anirudh is asking, sir, why minus 60 is 102's complement? Please repeat, sir. Anirudh, 1 second. I have already 1 second. Anirudh, hopefully you have not listened the theory lectures, so you're getting doubts. Anyway, see, 60, the representation is 32, 1648, then 8, 48, and 4, 60, yeah, 0, 0. So this is only 60. I mean, 60 in base 10 is equivalent to this in binary. Hopefully it is correct. 32, 1648, 12, yeah. So if I say it is plus 60, you have to add a sign bit, this is 0. But if I say it is minus 60, okay, if I say it is minus 60, you have to take 2's complement of this. So if you take 2's complement of this, what do you get? You get 0, get 0. Then you flip all the bits. That's the process to 0, 0, 1. Then you flip all the bits. Then you get 0, 0, 0, and 1. This is what is minus 60 in 2's notation. If I say what is minus 60 in 1s, you have to take 1s of this. So this is what the answers. But as I said, using sign bit extension, the sign bit is 1. So this one you can copy 1 time, 2 times, 3 times, 100 times towards left. It doesn't matter. That way minus 60 is coming. Access code, gray code. Yeah, access code, gray code, that comes in binary codes. If you see binary codes, it's in my chapter 6. So I haven't come to that. So I'm going to follow this sequence. Okay. So thank you. I'm closing the session here today. Tomorrow again, 6 o'clock, we'll meet with Boolean algebra and might be logic gate as well. Thank you.